Good wishes to all of you. Geography, Chapter 2, Geomorphology for UPSC audiobook. In this chapter, we have covered the topics of interior of the earth, origin of continents and oceans, earthquakes and volcanism, geomorphic processes, minerals and rocks, landforms and their evolution. Interior of the earth. The interior of the earth has long been shrouded in mystery. It is difficult to know how the earth came into being exactly and also about its interior. The estimates and inferences based upon the observations and data collected through tools like seismographs, volcanic activities, gravitational and rock studies have thrown light upon these aspects. The sources which provide knowledge about interior of earth can be divided into direct sources. These can be in the form of analysis of different types of rocks found at various depths, recovered from mines and drilling projects. Volcanic eruption forms another source of obtaining direct information. Indirect sources analysis of properties of matter like temperature, pressure, density, and gravitation, magnetic field, and seismic activity studies can indirectly provide information about the interior based on existing knowledge and estimates and interferences made based on various studies. Another source of information are the meteors, meteors that at times reach the earth as the material and the structure observed in the meteors are similar to that of the earth. Based on these studies, following observations has been made regarding the Earth's interior. The Earth is broadly divided into the three layers of crust, mantle, and core based on varying properties of material present at different depths. The material in the interior exists in different states at different depths like semi-solid, solid, liquid, molten, gaseous. The crust is solid. The asthenosphere in plastic, the mantle below the asthenosphere is mostly in solid state. The inner core is solid due to the amount of pressure that is exerted on it from above, whereas the outer core is in liquid state. Inside its interior, temperature and pressure increase with depth. You can look here the picture, interior of the earth, source vdocuments.mx. To scale, inner core, solid not to scale, 5100 kilometers, outer core, liquid 2900 kilometers, mantle, asthenosphere, lithosphere, crust and uppermost solid mantle, crust 0 to 100 kilometers thick. Crust. The crust is the outermost solid part of the earth. It is brittle in nature. The mean thickness of oceanic crust is 5 kilometers, whereas that of the continental is around 30 kilometers. Oceanic crust is thinner as compared to the continental crust. The continental crust is thicker in the areas of major mountain systems. The mean density of material in the continental crust is 2.7 grams by centimeter cube. It is predominantly composed of silica and aluminum in the upper layers of the Earth's crust. The oceanic crust is made up of heavier rocks having a density of 3 grams by centimeter cube. It is predominantly composed of silica and magnesium. The kind of rock seen in the oceanic crust is basalt. Crust is the source of soil on the lands, salts of the sea, gases of the atmosphere, and all the water of oceans, atmosphere, and land. Mantle. The portion of the Earth's interior beyond the crust is called the mantle. The mantle extends from Moho's discontinuity to a depth of 2900 kilometers. Moho discontinuity is the layer which separates the crust from the mantle. It is in a solid state. It has a density higher than the crust portion. Mean density is 4.6 grams by centimeter cube. Made of mafic, a word formed from ma, for magnesium bearing and FiC from ferric or iron bearing silicate minerals. The asthenosphere is the upper portion of mantle. The word astheno means weak. It is considered to be extended up to 400 kilometers and has a density higher than the crust, 3.4 grams by centimeter cube. It is the chief source of magma that finds its way to the surface during volcanic eruptions. The upper and lower mantle is separated by a layer known as repti discontinuity, which basically is around a depth of 700 kilometers. The lower mantle is hotter about 2800 degrees Celsius than the upper mantle about 1800 degrees Celsius, but it is largely rigid as a result of intense pressure at this depth. The crust and the uppermost part of the mantle are called lithosphere with a thickness of about 2200 kilometers. Relevance of mantle in interior of the earth. Mantle is the most voluminous portion of the earth's interior, occupying 83% of the earth's volume and around 68% of the total mass of the earth. It is also important regarding the landforms formed on the upper surface of the earth as whatever major endogenic forces operate. It is a mantle where the activity takes place. The upper portion, though not any fluidic stage, is highly malleable, as a result of which the plates move over this layer and there is creation of new landforms and the destruction of the old. The movement of the material inside the mantle is the convective currents. In this case, the material are transported from the lower part of the mantle to the upper part on account of being more heated. This leads to circulation of convective current from the bottom to the top and vice versa. These convective movements inside the mantle are believed to be the driving force behind the tectonic movements and is also a reason for the hotspot volcanism. Core. The core is made up of heavier metals which sank to the bottom at the very beginning when the earth was still in a molten state. The region is generally referred to as the barosphere. Upon subsequent cooling of the upper layers, the material is the core started to harden due to the pressure exerted by the overlying layers. This is the reason why the inner core is pure solid while the outer core is in a liquid state. Even though the volume and mass of the core is only 16% and 32% of the total volume and mass of the earth, the density increases to as much as twice that of the mantle. The core mantle boundary is located at a depth of 2900 kilometers. The Earth's core is about 3500 kilometers in radius and is very hot, somewhere between 3000 degrees Celsius and 5000 degrees Celsius. The density of material at the mantle core boundary is around 5 grams by centimeter cube, which increases to around 13 gram by cm cube at the center of the earth at 6300 kilometers. The core is made up of very heavy material, mostly composed of nickel and iron. Hence, it is also called the NiFe layer. The inner core is in the solid state, whereas the outer core is in the liquid state. The liquid iron core creates a magnetic field as the fluid flows around the solid core and interacts with the Earth's existing magnetic field. This process in turn generates a dynamic energy condition that maintains the Earth's perpetual magnetic field, geomagnetism. Discontinuous discontinuities in Earth's interior. Konar discontinuity lies between the upper and the lower crust. Mohorovic discontinuity lies between the lower crust and the upper mantle. Raptor discontinuity between upper and lower mantle. Juchenberg discontinuity lies between lower mantle and upper core. Lachman discontinuity lies between the outer and the inner core. Here we can see on this picture discontinuities in its interior, source brightly dotted. Connote discontinuity between upper and lower crust, upper mantle, mantle, outer core, inner core. Mohorovic discontinuity between lower crust and upper mantle. Repeated discontinuity between upper and lower mantle. Gutenberg discontinuity between lower mantle and outer core. Lehman discontinuity between outer and inner core. Origin of continents and oceans. Geologists and geographers over the long period of time have struggled to find justification regarding the present state of the earth, including the oceans and the continents. It also bothered them that the northern hemisphere is predominantly consisting of land and the southern hemisphere predominantly with the water bodies. Number of theories were proposed to explain the present distribution of oceans, continents and their topographic features such as mountains, trenches, etc. Some of the major theories include continental drift theory by Alfred Wegener, Postdrift theories, convection current theory, paleomagnetism, seafloor spreading, and plate tectonic theory. Continental drift theory. Alfred Wegener, in his continental drift theory, challenged the idea of permanency of continents and oceans and propounded that continents drifted over the ocean floor. According to Wegener, there was a there was the presence of a supercontinental called Pangaea in the Triassic period 250 million years ago. By the end of the Triassic period, the supercontinent started to break into two parts, Laurasia North and Gondwanaland South. By the end of the territory period, these two have further broken into a number of subparts and drifted away from each other to present locations. Permian 250 million years ago, Pangaea Triassic 200 million years ago, Laurasia, Tethys, Gondwanaland. Jurassic 145 million years ago, Cretaceous 65 million years ago, present day. Position of continents throughout geological past, source US Geological Survey. Wegener presented a set of evidence in support of his theory. Shape of continents. The coastlines of South America and Africa fronting each other have a remarkable and unique match. In 1964, Bullard created a map using a computer program to find the right fit of the Atlantic margin, and it proved to be a quite fit. Rocks of the same age across the oceans. The radiometric dating methods have helped in correlating the formation of rocks present in different continents across the ocean. The ancient rocks built in the coast of Brazil match with those found in Western Africa. The old marine deposits found on the coasts of South America and Africa belong to the Jurassic age. This implies that the Atlantic Ocean never existed there before that time. Fossil evidence. Wegener used already documented fossil evidence of Mesozoic life forms. For example, the fossils of Mesosauric, a small reptile, was found only in two places, South Africa and Brazil. Continental drift seems to be the only logical explanation to this finding. Placer deposits. The presence of abundant placer deposits of gold along the Ghana coast and the complete lack of its sources rocks in the area is a phenomenal fact. The gold bearing veins are present in Brazil, and it is evident that the gold deposits of Ghana in Africa are obtained from the Brazil plateau from the time when the two continents were beside each other. Paleoclimatic evidence. Tillite is a sedimentary rock made from glacier deposits. The Gondwana system of sediments from India is recognized as having its counterparts in 6 different landmasses in the southern hemisphere. Counterparts of this series are found in Madagascar, Africa, Antarctica, Falkland Islands, and Australia, not to mention India. At the base, the system has thick tillite signifying widespread and sustained glaciation. Here you can look in this figure continental drift, source US Geological Survey, Africa, South America, Antarctica, Australia, India. Fossils evidence of the Triassic land reptile Lystrosaurus. Fossils of the fern Glossopteris found in all of the southern continents show that they were once joined. Fossil remains of the freshwater reptile Mesosaurus. Fossil remains of Cynonchus, a Triassic land reptile approximately 3 meter long. Wegener suggested that the polar fleeing force due to Earth's rotation and the tidal force due to the gravitational pull of the Sun and Moon are responsible for the drifting of continents northward. But later studies suggested that both these forces are too weak to account for continental drift, and even if accounted for, they would have rather stopped continents from drifting. These shortcomings paved the way for the other studies, post-drift studies. Post-drift studies, convection, current theory. You can look in this figure, convection current in the mantle. Source ucmp.berkeley.edu. Trench, ridge, trench. Slab pull, lithosphere. 700 kilometers. Mantle, atmosphere. Post-drift studies, convection current theory. Intense heat is generated in the mantle due to radioactive substances causing thermal differences in the mantle. Arthur Holmes suggested that convection currents are generated due to these thermal differences. He also postulated that through the convection currents mechanism, heat distribution takes place in the mantle. The convection currents occupy the entire mantle, and when rising limbs of these currents meet, they put a frictional drag on the base of lithospheric plates, and divergence of lithospheric plates occur and falling limbs result in convergence of plates. Paleomagnetism. Paleomagnetism refers to the study of ancient geomagnetism that was recorded in the rocks formed during that period. Several rocks, such as basalt, contain magnetic minerals, and these magnetic minerals align themselves in the direction of Earth's magnetic field present at the time of rock formation solidification. These rocks acquire geomagnetic properties associated with their formation period and thus act as a natural record of Earth's geomagnetic properties, including magnetic field of Earth. Paleomagnetic studies have proved that orientation of Earth's magnetic field has frequently altered over time. Paleomagnetism provided strong evidence in support of seafloor spreading and plate tectonics. The regions along mid-oceanic ridges (MOR) hold a unique record of Earth's magnetic field. Paleomagnetic studies revealed that along mid-oceanic ridge, rocks with alternate patterns of magnetic properties are found on both sides of the ridge. MOR is a region of diverging plate boundary. As a result, when the plates move apart, magma from below rises through fissures and solidifies along the narrow band of rocks on either side of the vent, and also while cooling, the rocks acquire the Earth's magnetic field present during that period. As the convection currents pull the oceanic plates apart, the solidified band of rocks move away from the vent and new magma rises and solidifies along narrow bands of rocks next to MOR. This process continues for millions of years and during which the magnetic field of Earth reverses. Thus, adjacent rock bands have opposite polarities. This process repeats over and over again, giving parallel bands on either side of MOR and an alternate pattern of magnetic stripping on the seafloor. Take a look at this figure. Alternate pattern of magnetic strips along seafloor, source Britannica, normal magnetic polarity, reversed magnetic polarity. Here you can see A, B, lithosphere magma. Seafloor spreading. Harry Hess propounded the hypothesis known as the seafloor spreading in the 1960s based on ocean floor and paleomagnetic studies. According to him, MORs are regions on Earth's surface located directly above rising limbs of convection currents flowing in the mantle. Convection currents put a frictional drag on the base of oceanic crust and force them to spread laterally in the opposite direction, that is, divergence of plates. This leads to volcanism along MOR and causes creation of oceanic crust. MORs are the areas of creation, whereas trenches are the areas of destruction of oceanic crust. Trenches are regions where subsiding limbs of convection current drag oceanic crust into the mantle. This process continues and new oceanic crust forms at MORs as the old one gets destroyed at trenches. The fact that the oceanic crust is very much younger than continental crust adds validity to this theory. Take a look at this figure. Seafloor spreading. Credits Ellen Mudgett, UCMP. You can see here convection currents in mantle, convergent boundary volcanoes trench, mid-oceanic ridge, divergent boundary trench, continent transform fault, subducting plate, lithosphere rising magma earthquake, melting. You can see here the process on a picture format. Plate tectonic theory (PTT). In 1967, MC, Kenzie, and Parker and also Morgan independently collected the available ideas and came out with another concept termed plate tectonics. Plate tectonics is nothing but movement of lithospheric plates due to internal forces emanating from Earth's interior. Lithosphere consisting of crust and top mantle is broken into a network of distinct plates referred to as lithospheric plates. A lithospheric plate is a massive, irregularly shaped slab of solid rock, generally composed of both continental and oceanic lithospheres. Plates move, float over the atmosphere as rigid units and interact with each other, leading to tectonic activity. According to plate tectonic theory, Earth's lithosphere is divided into seven major and some minor plates. Major tectonic plates include Antarctica and surrounding oceanic plate, North American plate, South American plate, Pacific plate, India, Australia, New Zealand plate, African with the Eastern Atlantic floor plate, Eurasian and adjacent oceanic plate. Minor tectonic plates, Caucasus plate between Central America and Pacific plate, Nazca plate between South America and Pacific plate, Arabian plate, Saudi Arabian landmass, Philippine plate between Asiatic and Pacific plate, Caroline plate between Philippine and Indian plate, Fusey plate northeast of Australia, Caribbean plate, Juan de Fuca plate between North America plate and Pacific plate. Take a look at another figure. Major and minor plates of the world. Source NCRT. Eurasian plate, North American plate, Mid-Atlantic ridge, Eurasian plate, African plate, Caribbean plate, Cocos plate, East Pacific rise, San Andreas fault, Atlantic trench, Caroline plate, Java trench, Indo-Australian plate, Nazca plate, South America plate, Scotia plate, Antarctica plate. Divergent boundary, convergent boundary, transform boundary are mentioned here. Plate boundaries. Plate boundaries are the regions where plates interact with each other. Geographical features and phenomena such as mountains, trenches, mid-oceanic ridges, volcanism, earthquakes are direct consequences of interactions between various plates. There are three types of plate boundaries. Divergent plate boundaries. Plates move away from each other, resulting in formation of faulting and gaps. Magma moves upwards to fill the gap, leading to volcanism and formation of new crust. Divergent plate boundaries are also known as constructive boundaries as new crust is formed at this boundary. Earthquakes and volcanic activity are very common along divergent boundaries. Mid-Atlantic ridges are found at divergent boundaries. Here you can see the figure. Divergent plate boundaries source geology phase plate atmosphere. The directions are opposite. Convergent plate boundaries. They are also known as destructive plate boundaries. Here plates move towards each other causing collision and subduction of the denser plate under the lighter plate. Convergent plate boundaries source geology base. Plates are on the same side direction. There are three types of convergence. Ocean convergence. When two oceanic plates converge, the heavier and denser oceanic plate subducts under less dense oceanic plate, forming trenches along the boundary. The subsiding plate material can melt and become magma, which tends to rise. This upward moving magma creates volcanic landforms along the boundary. Island arcs are a chain of volcanic islands formed at the boundary. Japan, Philippines, Indonesian islands are examples of volcanic landforms formed due to ocean convergence. Ocean continental convergence when an oceanic and continental plate converge, denser oceanic plate subducts under lighter continental plate forming a trench along the boundary. Trenches here are not as deep as in OO convergence. Continent ocean convergence is similar to ocean ocean convergence except that in continent ocean convergence, mountains are formed instead of islands. Example, Andes and Rockies are mountain ranges formed due to ocean continent convergence. Continent continent convergence. In most cases of continent continent plate convergence, neither plate subducts, and even if one of the plates subducts, the subduction zone will not go deeper than 40 to 50 kilometers. Convergence leads to collision and deformation of plates along boundaries, leading to formation of fold mountains. Example, Himalayas formed due to the collision of Eurasian and Indian plates. Transform plate boundaries. Here, lithosphere plates slide past one another without separating or converging. The two plates are in contact along a vertical fracture called a transform fault. Transform plate boundaries source geology base. Here plates slide horizontally to each other. They move parallel to each other without causing any construction or destruction but only deformation of existing landform. San Andreas Fault along eastern coast of Pacific Ocean is the best example of a transform fault. Taking a look at this figure, types of plate boundaries credits USGS. Convergent plate boundary, trench, island arc, stratovolcano. Transform plate boundary, oceanic spreading ridge, shield volcano, hotspot, lithosphere, ethnosphere, oceanic crust, subducting plate, continental crust. And divergent plate boundary, oceanic spreading ridge. Convergent plate boundary, trench. Continental rift zone, young plate boundary. Plate tectonics theory forms the core of the modern geological paradigm that helps explain many seemingly unrelated geological phenomena. It provided a uniform context for understanding mountain building processes, volcanoes, and earthquakes, as well as the evolution of Earth's surface and reconstructing its past continents and oceans. Formation of most of the major landforms can also be satisfactorily explained using PTT. Hotspots and mantle plumes. Mantle plumes are areas where heat and or rocks in the mantle are rising towards the surface. A hot spot is the surface expression of the mantle plum. Hot spots result from hot, narrow plumes of material that rise from deep within the mantle. As the hot mantle plum reaches the base of the lithosphere, it spreads laterally. The lateral spreading of the hot mantle helps to move the Earth's rigid outer plates. Heat from this extra hot magma causes melting and thinning of the rocky crust, which leads to widespread volcanic activity on Earth's surface above the plum. About 95% of the world's volcanoes are located near the boundaries of tectonic plates. The other 5% are thought to be associated with mantle, plumes, and hotspots. Hotspot sea mounts that reach the surface of the water can create entire chains of islands, such as the US state of Hawaii. Scientists think that this volcano chain of islands has been forming for at least 70 million years over a hotspot underneath the Pacific plate. Hotspots can also develop beneath continents. The Yellowstone hotspot, USA, for example, has produced a series of volcanic features that extend in a northeastern direction. Earthquakes and volcanism. Earthquake. Introduction. An earthquake, in simple words, is the shaking of the earth. It is a manifestation of the power of tectonic forces, endogenetic. It is the result of the release of energy caused due to transient disturbance of the elastic or gravitational equilibrium of the rocks at or beneath the surface of Earth. The release of energy generally occurs along a fault sharp break in the crustal rocks. Rocks along a fault tend to move in opposite directions, but the friction due to overlying rock strata locks these rocks together. The point inside the earth where the energy is released is called the focus or hypocenter of an earthquake. The release of energy generates waves. These energy waves traveling in different directions reach the surface. The point on the Earth's surface nearest to the focus is called the epicenter. Seismology is the study of earthquakes and seismic waves. About 68% of all earthquakes observed in the vast regions of the Pacific Ocean are a ring of fire and are closely linked with crustal dislocation and volcanic phenomena. Earthquake waves, seismic waves, these are the energy waves generated by an earthquake. Seismic waves may travel through the Earth's interior, called body waves, P and S waves, or either along or near the Earth's surface, called surface waves. Rayleigh and Love waves. The study of seismic waves provides information about layered interiors. These waves are basically of two types. Body waves. These are generated due to the release of energy at the focus. These waves move in all directions traveling inside the body of the earth. Types of body waves. P wave. These are also called primary waves. P waves are faster among seismic and are the first to arrive at the surface. These are similar to sound waves. They can travel through gaseous, liquid, and solid materials. P wave or compressional wave vibrates parallel to the direction in which the wave is traveling. This exerts pressure on the material in the direction of the propagation. Hence, it creates density differences in the material leading to stretching and squeezing of the material. Ground is shaking this way, P waves. Waves are traveling this way. S waves or secondary waves. As an S wave or shear wave is a seismic body wave that shakes the ground back and forth perpendicular to the direction the wave is moving. S waves arrive at the surface with some time lag after P waves. These waves can travel only through a solid medium. As waves vibrate perpendicular to the direction of the wave in the vertical plane, creating throats and crests in the material through which they pass. Difference between P waves and S waves. P waves are the first wave to hit the Earth's surface. S waves, these arrive after P waves. P waves travel in the speed range of 1.5 to 13 km per square. S waves are almost 1.7 times slower than P waves. P waves can travel through solid, liquid, and gas. S waves travel through only solids. Shadow zone of earthquake waves. Earthquake waves travel in all directions from the focus, which is recorded by seismographs located at far off locations. There exist some specific areas where seismic earthquake waves are not recorded on a seismograph. Such a zone is called the shadow zone. It is a well established fact from various observations that seismographs located at any distance within 105 degrees from epicenter record the arrival of both P and S waves. However, the seismographs located beyond 145 degrees from epicenter record the arrival of P waves but not that of S waves. The entire zone beyond 103 degrees does not receive S waves. Hence, the shadow zone of the S wave is much larger than that of the P waves. Thus, a zone between 103 degrees and 145 degrees from epicenter was identified as the shadow zone for both the types of waves. Here you can see on picture P wave shadow zone, P wave ray paths 105 degrees, core, P wave shadow zone 105 degrees to 145 degrees. P wave is received here. And now we have to look at S waves, surface waves. Take a look at this picture first. S wave shadow zone, quark, core. P wave ray paths 103 degrees, S wave shadow zones. No direct S waves received here. Surface waves. The body waves interact with the surface rocks and generate a new set of waves called surface waves. These waves move along the Earth's surface, hence the name. These waves are the last to log on a seismograph. Surface waves are considered to be the most destructive waves. Types of surface waves. Surface waves are classified by the type of motion they transmit into rayleigh wave. It is a seismic surface wave causing the ground to shake in an elliptical motion with no transverse or perpendicular motion. It has an up and down rolling motion and is also called surface rolling waves. Rayleigh wave. Love wave. Here you can see on picture. It is a surface wave having a horizontal motion that is transverse or perpendicular to the direction in which the wave is traveling. The amplitude of ground vibration caused by a love wave decreases with depth. Measuring earthquakes. The earthquake events are measured either according to the magnitude or intensity of the shock. Mercalli scale. The intensity scale is named after Mercalli, an Italian seismologist. It takes into account the visible damage caused by the event. The range of intensity scale is from 1 to 12. Richter scale. The magnitude scale is known as the Richter scale. The magnitude relates to the energy released during the quake. The magnitude is expressed in absolute numbers 0 to 10. Types of earthquakes. Tectonic earthquakes. These are generated along a fault plane due to the sliding of rocks. The most common ones are the tectonic earthquakes. Volcanic earthquakes. These are generated due to violent volcanic eruptions. However, these are confined to areas of active volcanoes. Collapse earthquakes. Sometimes the roofs of underground mines collapse, causing minor tremors. These are called collapse earthquakes. Explosion earthquakes. Tremors may also occur due to the explosion of chemical or nuclear devices. Such tremors are called explosion earthquakes. Reservoir induced earthquake. The earthquakes that occur in the areas of large reservoirs are referred to as reservoir induced earthquakes. Earthquake swarms. An earthquake swarm is a sequence of seismic events occurring in an area without a major earthquake within a relatively short period of time. The period used to define the swarm can vary, but generally is of the order of days, months, or even years. Example, earthquakes associated with volcanic activity often occur in swarms. Global distribution of earthquakes. Earthquakes are found along all types of plate boundaries. Circum-Pacific Belt. This belt is along a path surrounding the Pacific Ocean. This zone includes the regions of great seismic activity such as Japan, the Philippines, and Chile. This path coincides with the Pacific Ring of Fire. Alpine Himalayan belt. Another major concentration of a strong seismic activity runs through the mountainous regions that flank the Mediterranean Sea and extends through Iran and on past the Himalayan mountains. Mid-Atlantic Ridge, a mid-ocean ridge that extends along the floor of the Atlantic Ocean in southern Europe. Take a look at this first figure, global distribution of earthquakes. Tectonic plate boundaries, global earthquakes depth kilometers. It was mentioned here clearly, convergent, extensional, transform, subduction. And colors also mentioned here. Earthquake zones in India. Indian subcontinent has a long history of devastating earthquakes, partially due to the fact that India is driving into Asia at a rate of approximately 47 millennium year. As per Bureau of Indian Standards (BIS), India has been divided into four seismic zones with Zone 2, 3, 4, and 5, unlike its previous versions, which consisted of 5 zones for the country. After some revisions in the previous zoning, Zone 1 was altogether removed. Here you can see in this picture seismic zones of India. Zone 2 are mentioned in blue color, Zone 3 in radium color, Zone 4 in light orange color, Zone 5 in red color. Here the Zone 2 was percentage in 40.93, Zone 3 30.79, Zone 4 17.49, Zone 5 10.79. Seismic Zone Map of India 2002. About 59% of the land area of India is liable to seismic hazard damage. Zone intensity. Zone 5 very high risk zone. Area liable to shaking intensity 9 and above. Zone 4 high risk zone intensity 8. Zone 3 moderate risk zone intensity 7. Zone 2 low risk zone 6 and lower. Volcanism. A volcano is a vent or fissure in the crust through which hot gases, molten lava, mud flows, some rock fragments, and ash erupts outward from the interior of the earth. Volcanoes are located on or near plate boundaries. Subduction zones around the Pacific Rim have significant volcano activity, and that's why it is aptly named as the Pacific Ring of Fire. Mid-oceanic ridges, divergent plates, and certain hotspots also generate volcanic activity. Underground molten mineral matter is called magma. When magma cools and solidifies below the Earth's surface in the gaps, it creates intrusive topographic features like batholiths, laccoliths, phaccoliths, lopoliths, silly, dikes, etc. When the magma reaches the surface of Earth is called lava. This lava cools and hardens, building the extrusive volcanic landforms like cones, craters, calders, domes, and even lava plains. Here you can see clearly on this picture volcanism. Here you can look at the surface batholith, stalk, dike, laccolith, sill, diatreme, country rock, volcanic conduit, lava flow, eroded, laccolith ash flows, caldera with a cinder cone on floor, volcanic neck with radiating dikes, ash cone with volcanic dome, lava plate, cinder cone, lava mesa, composite volcano. Volcanic material, vapor and gases, steam and vapors, around 60 to 90% of gases erupted. Other gases such as carbon dioxide, nitrogen dioxide, sulfur dioxide, and sometimes sulfurated hydrogen, hydrochloric acid, etc., are erupted. Magma and lava. Felsic lava, usually very thick with a high viscosity. Lava does not usually flow very far from the volcano's vent and builds up steep slopes. Ejected pyroclastic material or tephra from volcanoes fall on the area surrounding the crater, creating a cone shape. Associated rocks are rhyolite and andesite. The most common type of volcano associated with felsic magma is the stratovolcano, sometimes called a composite volcano. Mafic lava, basalt. In contrast to felsic lava, it is not very viscous and holds little gas. Eruptions are usually quiet. The lava can travel long distances and spread out in thin layers. Large basaltic volcanoes typically have rounded domes and gentle slopes. The most common type of volcano associated with mafic lava is the shield volcano. Magma and lava can also be classified based on the percentage of silica into 1 acidic higher percentage of silica, 2 basic lower percentage of silica. Pyroclastic material or tephra, ejected particles of different sizes known collectively as pyroclastic material or tephra. Volcanoes can be classified on the basis of the nature of eruption, explosiveness at the form, shape, size developed at the surface. This in turn depends on the type or nature of magma involved, which is generally felsic, rich in iron and aluminium, or mafic, rich in magnesium and iron. Basic types of volcanoes. Shield volcanoes. A shield volcano is a type of volcano usually built of very fluid lava flows. Slopes are not steep. Shield volcanoes are built by effusive eruptions which flow out in all directions. Characterized by no or low explosivity with the basic lava simply flowing out. They can become explosive if somehow water gets into the vent. Bearing the basalt flows, the shield volcanoes are the largest of all the volcanoes on the earth. The Hawaiian volcanoes are the most famous examples. The upcoming lava moves in the form of a fountain and throws out the cone at the top of the vent and develops into cinder cones. Mauna Loa shield in Hawaiian volcanoes. Cinder cones. Cinder cones are small volcanoes. These are rarely more than a few hundred meters high. These form when frothy blobs magma is ejected under high pressure from a narrow vent producing tephra. The tephra accumulates around the vent to form a roughly circular hill with a central crater. Example is Wizard Island Oregon. Composite volcano, sometimes called a stratovolcano volcano, characterized by eruptions of cooler and more viscous lavas than that of basalt. Volcano eruptions are explosive as felsic magma can contain gases under high pressure. Stratovolcanoes are tall, steep cones built of layers of felsic lava and volcanic ash. In eruptions along with lava, large quantities of pyroclastic material and ashes find their way to the ground. These erupted materials accumulate in the vicinity of the vent openings leading to formation of layers, and this makes the mounds appear as composite volcanoes. Example, many active stratovolcanoes lie within the circum-Pacific mountain belt volcanic arc of Sumatra and Java. Caldera, most explosive among all volcanoes, these are so explosive that when they erupt, they tend to collapse on themselves rather than building any tall structure. The collapsed depressions are called calderas. The magma chamber supplying the lava is a huge and enclosed vicinity. Flood basalt provinces. From due to eruptions from a volcanic hotspot, pouring enormous volumes of basaltic lava that emerged from numerous vents and fissures and accumulate layer upon layer. These basalt layers, called flood basalts, can become thousands of meters thick and cover thousands of square kilometers. Example, the Deccan Traps in India. Volcanoes can also be classified based on periodicity of eruptions into categories. Active. An active volcano is one which has recently erupted and there is a possibility that it may erupt soon. Example, Mount St. Helens, United States. Barren Island, the only active volcano in India. Dormant. A dormant volcano is one which has not erupted in a long time, but there is a possibility it can erupt in the future. Example, Vesuvius in Naples, Italy. Extinct. An extinct volcano is one which has erupted thousands of years ago and there is no possibility of an eruption. Example, Mount Tillerson in Oregon. Introduction. The Earth's surface is being continuously subjected to by external forces induced basically within the Earth's atmosphere and by internal forces from within the Earth. The external forces are known as exogenic forces and the internal forces are known as endogenic forces. The actions of exogenic forces result in wearing down, degradation of relief, elevations and filling up, aggradation of basins depressions on the Earth's surface. The phenomenon of wearing down of relief variations of the surface of the Earth through erosion is known as gradation. The endogenic forces continuously elevate or build up parts of the Earth's surface and hence the exogenic processes fail to even out the relief variations of the surface of the Earth. So variations remain as long as the opposing actions of exogenic and endogenic forces continue. In general terms, the endogenic forces are mainly land building forces and the exogenic processes are mainly land wearing forces. Geomorphic process. The endogenic and exogenic forces causing physical stresses and chemical actions on earth materials and bringing about changes in the configuration of the surface of the earth are known as geomorphic processes. Diastrophism and catastrophism, volcanism, and earthquakes are endogenic geomorphic processes. Weathering, mass wasting, erosion, and deposition are exogenic geomorphic processes. Geomorphic agent. Any exogenic element of nature like water, ice, wind, etc., capable of acquiring and transporting earth materials can be called a geomorphic agent. These elements of nature become mobile due to gradients in fact of all the Movements either within the earth or on the surface of the earth occur due to gradients. From higher levels to lower level, from high pressure to low pressure areas, etc. Endogenic processes, the forces maintaining within the earth are called endogenic forces. The energy emanating from within the earth is the main force behind endogenic geomorphic processes. This energy is mostly generated by radioactivity within the interior of earth, rotational and tidal friction and primordial heat from the origin of the earth. This energy due to geothermal gradients and air flow from within induces endogenic forces causing contraction and expansion of rocks, which in turn leads to horizontal and vertical movements. The endogenetic forces can be divided into two categories: sudden movements, catastrophism. These forces work very quickly and the result can be seen in the minutes. For example, volcanic eruptions and earthquakes. It should be noted that the sudden movements due to these forces are the result of long term changes within Earth, only their cumulative effect is sudden. Diastrophism, all processes that move, elevate, or build up portions of Earth's crust come under diastrophism. These are also called as continental building processes. These forces operate very slowly and their effect can be seen after thousands of years. They are further subdivided into two categories: aperogenetic processes involving uplift or warping of large parts of the Earth's crust causing large scale upliftment or submergence of land areas. Aperogenetic movements can be divided into two types. Upward movement. Upward movement causes upliftment of continental masses in two ways: the upliftment of the whole continent or part thereof, the upliftment of coastal land of the continents. Such a type of upliftment is called emergence. Downward movement. Downward movement causes subsidence of continental masses in two ways: subsidence of land area. Such a type of downward movement is called as subsidence. Alternatively, the land area near the sea coast is moved downward or subsided below sea level and thus submerged under sea water. Such a type of downward movement is called submergence. Orogenic or the mountain building movements act tangentially to the Earth's surface, causing severe folding and affecting long and narrow belts of the Earth's crust. Orogenic movements processes cause more complicated deformation in the Earth's crust than the aperogenetic forces. Orogenic forces work in two ways: in opposite direction, divergent force. Therefore, when this force operates in opposite directions, tensional forces create rupture, cracks, fracture, and faults in the crustal parts of the earth towards each other. Convergent force. This is called compressional force. The compressional force causes crustal bending leading to formation of folds. Mountains. Mountains are important geomorphological features on the surface of Earth, occupying nearly 27% of the world's land surface. They are manifestations of organic forces. According to the US Geological Survey, there is no official difference between hills and mountains, but generally they are differentiated on the basis of height. A mountain is any natural elevation rising considerably higher, above 600 meters, than the surrounding area, whereas a hill is a land surface that rises higher than the surrounding area but not more than 600 meters. Mountains generally have a small summit and a broad base. They vary in their heights, like they can be as high as Mount Everest, which has an elevation of 8,850 meters, and as low as Mahul in Thane district of Maharashtra with a height around 852 meters. They also vary in shape and their composition based on how they are formed, like volcanic mountains can have different shape and mineral composition than fold mountains. There are four main types of mountains. Fold mountains. Fold mountains are created by intense compressional or convergent endogenic forces that cause crustal wrapping or folding. The upward rise of the crustal part due to compressive convergent force is called up wrapping, and while bending of crustal part downwards forming a basin or depression is called down wrapping, whereas fold effectively shortens its crust, creating waves like bends called folds. The upfolds are called anticlines and downflows as synclines. Due to the complexity in compressional forces, the fold mountains show complicated folds like shown below. Take a look at this image. Types of fold: axis, anticline, syncline, asymmetrical fold, overfold, recumbent fold. Types of fold. They are by far the most widespread mountains, and many of the world's biggest mountain belts, such as the Himalayas, Rockies, Andes, Alps, etc., are examples of fold mountains. Due to their great heights, these mountains are also called mountains of elevation. Block mountains. Sharp break in the crustal rocks is called a fault. These breaks are caused due to the cracks developed in the Earth's crust, mostly due to tensional force which tends to pull the crust apart. The plane along which rock blocks get displaced is called a fault plane. Block mountains are created when large areas are broken and displaced vertically along a fault. The uplifted blocks are termed as horsts and the lowered blocks are called graben. The Rhine Valley, the Great African Rift Valley floor is graben. The Vosges Mountain in Europe are examples of such mountain systems. You can see here Horst Graben. Volcanic mountains. Volcanic mountains are the accumulations of large amount of volcanic lavas and pyroclastic material around the volcanic vent, such as sea amounts, and stratovolcanoes. They are also called mountains of accumulations. They can be of different shapes and sizes like cinder, shield, composite, etc. Residual or relic mountains. These are formed due erosions by various geomorphic agents. Some rocks areas may remain resistant to erosion when the general level of land is lowered by the agents of denudation, forming residual or relic mountains. Example: Monadnock, USA. These can also form when a river cuts through a plateau like that in the highland of Scotland and Scan- Scandinavia. Palkonda, Prasant, and Rajmahal, Girnar Hills are examples. Exogenic processes or denudation processes. All the oxygenic All the exogenic geomorphic processes are covered under a general term denudation. The word denude means to strip off or to uncover. Weathering, mass wasting, movements, erosion, and transportation are included in denudation. The exogenic processes derive their energy from the atmosphere determined by the ultimate source of energy, that is the sun, and also the gradients created by tectonic factors. Here you can see on this denudation denudational processes. that are divided into three: weathering, mass movements, erosion, transportation. This is the process on the first step, and second step is driving force energy. Weathering is divided into gravitational, molecular, circus, and or chemical actions. Mass movements are divided gravitational force, erosion, erosion or transportation, kinetic energy. Weathering. Weathering is defined as a mechanical disintegration and chemical decomposition of rocks through the actions of various elements of weather and climate. As very little or no motion of materials takes place in weathering, it is an in situ or on site process. Weathering processes are affected by many complex geological, climatic, topographic, and vegetative factors. There are three major groups of weathering processes: chemical, physical, or mechanical, biological weathering processes. Generally, these processes operate in combination at a particular place, but quite often a dominance of the process can be seen. Chemical weathering, a group of weathering processes with solution, carbonation, hydration, oxidation, and reduction act on the rocks to decompose, dissolve, or reduce them to a fine clastic state through chemical reactions by oxygen, surface, and or soil, water, and other acids. Solution: when something is dissolved in water or acids, the water or acid with the dissolved content is called solution. This process involves removal of solids in solution and depends upon solubility of a mineral in water or weak acids. On coming in contact with water, many solids disintegrate and mix up as suspension in water. Carbonation. Carbonation is the reaction of carbonate and bicarbonate with minerals and is a common process helping the breaking down of feldspars and carbonate minerals. Hydration. Hydration is the chemical addition of water. Minerals take up water and expand. This expansion causes an increase in the volume of the material itself or rock. Oxidation. In weathering, oxidation means a combination of a mineral with oxygen to form oxides or hydroxides. The minerals most commonly involved in this process are iron, manganese, sulfur, etc. Reduction. When oxidized minerals are placed in an environment where oxygen is absent, reduction takes place. Such conditions exist usually below the water table in area of stagnant water and waterlogged ground. Red color of iron upon reduction turns to greenish or bluish gray. Physical weathering process. Physical or mechanical weathering processes depend on some applied forces. The applied could be gravitational forces such as overburden pressure, load, and shearing stress. Expansion forces due to temperature changes, crystal growth, or animal activity. Water pressures are controlled by wetting and drying cycles. Most of the physical weathering processes are caused by thermal expansion and pressure release. Unloading and expansion. Removal of overlying rock load because of continued erosion causes vertical pressure releases with the result that the upper layers of the rock expand producing disintegration of rock masses. Temperature changes and expansion. With rise in temperature, every mineral expands and pushes against its neighbor, and as temperature falls, a corresponding contraction takes place: freezing, thawing, and frost wedging. Frost weathering occurs due to growth of ice within pores and cracks of rocks during repeated cycles of freezing and melting. This process is most effective at high elevations in mid latitudes where freezing and melting is often repeated. Glacial areas are subject to frost wedging daily. In this process, the rate of freezing is important. Rapid freezing of water causes its sudden expansion and high pressure. The resulting expansion affects joints, cracks, and smaller intergranular fractures to become wider and wider till the rocks breaks apart. Salt weathering. Salts in rocks expand due to thermal action, hydration, and crystallization. Many salts like calcium, sodium, magnesium, potassium, and barium have a tendency to expand. Biological weathering. It is contribution to or removal of minerals and ions from the weathering environment and physical changes due to growth or movement of organisms. Burrowing and wedging by organisms like earthworms, termites, rodents, etc., help in exposing the new surfaces to chemical attack and assists in the penetration of moisture and air. Human beings, by disturbing vegetation, plugging, and cultivating soils, also help in mixing and creating new contacts between air, water, and minerals in the earth materials. Significance of weathering. Weathering is an important process in the formation of soils. Weathering of rocks and deposits helps in the enrichment and concentrations of certain valuable ores of iron, manganese, aluminium, copper, etc., which are of great importance for the national economy. Mass movements. These movements transfer the mass of rock debris down the slopes under the direct influence of gravity. The movements of mass may range from slow to rapid, affecting shallow to deep columns of materials and include creep, flow, slide, and fall. Gravity exerts its force on all matter, both bedrock and the products of weathering. So, weathering is not a prerequisite, prerequisite for mass movement, though it aids mass movements. Mass movements do not come under erosion, though there is a shift aided by gravity of materials from one place to another. Weak, unconsolidated materials, thinly bedded rocks, faults, sleepy, dipping beds, vertical cliffs, or steep slopes, abundant precipitation, and torrential rains, and scarcity of vegetation, etc. Favor mass movements. Three types of mass movements: very slow, fast and dry, fast and wet. Very slow, soil creep, solidification, solidification, sorry, solifluction. Fast and dry, rockfall, avalanche. Fast and wet, mud flow, earth flow, landslide, slumps. Here you can see on this picture types of mass movements: rotational landslide, translation landslide, block slide, rock fall, topple, debris flow, debris avalanche, mud flow, slide, creep. Erosion and deposition. Erosion, it involves acquisition and transportation of rock debris. When massive rocks break into smaller fragments through weathering and any other process, erosional geomorphic agents like running water, groundwater, glaciers, wind, and waves remove and transport it to other places depending upon the dynamics of each of these agents. Abrasion, scraping, or wearing by rock debris carried by these geomorphic agents also aids greatly in erosion. By erosion, relief degrades, that is, the landscapes is worn down. That means, though weathering aids erosion, it is not a precondition for erosion to take place. The erosion and transportation of earth material is brought about by wind, running water, glaciers, waves, and groundwater. Of these, the first three agents are controlled by climatic conditions. The work of the other two agents of erosion. The work of the other two agents of erosion. Waves and groundwater is not controlled by climate. In case of waves, it is the location along the interface of litho and hydrosphere coastal region that will determine the work of waves. The work of groundwater is determined more by the lithological character of the region. The karstography sorry the crash topography develops in regions where rocks are permeable and soluble in water. Deposition is a consequence of erosion. The erosional agents lose their velocity on gentler slopes and the materials carried by them start to settle themselves. The coarser materials get deposited first and finer ones later. By deposition, deposits get filled up. The same erosional agents with running water, glaciers, wind, waves, and groundwater act as aggradational or depositional agents also. Rocks. There is a close relation of rocks with the landforms, soils, and minerals of a region. So, basic knowledge of rocks is imperative for geographical studies. The Earth's crust is composed of rocks of various types differing in texture, structure, permeability, mode of formation, etc. A rock is an aggregate of one or more minerals. Minerals are the naturally occurring substances which is composed of two or more elements. Different types of rocks are worn down, eroded at different rates. Some are easily eroded, whereas others are much more resistant. Their erosion depends upon the structure, composition, and stage time. Rock may be hard or soft and can be of varied colors. For example, granite is hard, soapstone is soft, gabbro is black, and quartz can be milky white. There are different kinds of rocks and based on their mode of formation or origin, the three broad classes of rocks are igneous rocks. Igneous is a Latin word meaning fire. Sedimentary rocks, Latin word sedimentum. Metamorphic rocks, Greek word metamorphos meaning change of form. Porous rocks, rocks which can absorb water, they are usually soft. Non-porous rocks, rocks which do not absorb water or absorb very less water. They are usually hard. Permeability, it is a measure of the ease with which a fluid, water in this case, can move through a porous rock. Texture, it is basically the size, shape or arrangement of the grains or crystals. Fossils, the remains of the dead plants and animals trapped in the layers of rocks are called fossils. Igneous rocks, they are also called volcanic rocks as these rocks are formed from the cooling, solidification and crystallization of hot and molten materials, that is magma. They are known as primary rocks or parent rocks as they were the first to form, and the other two types of rocks, sedimentary and metamorphic, are derived from them. Granite, gabbro, pegmatite, basalt, volcanic, breccia, and tuff are some of the examples of igneous rocks. Igneous rocks are classified based on texture. The texture depends upon the size and arrangement of grains or other physical conditions of the materials. If a molten material is cooled slowly at great depths, mineral grains may be very large. Sudden cooling at the surface results in small and smooth grains. Intermediate conditions of cooling would result in intermediate sizes of grains making up igneous rocks. Based on the rate and place of cooling, igneous rocks are divided into two types. Extrusive igneous rocks. The rocks cool quickly and as a result these rocks are fine grained. They are formed on the surface of the earth. Here magma has less time to form granules, crystals. Basalt, tuff, pumice are examples of extrusive igneous rock. Intrusive igneous rocks. These rocks are formed when magma cool slowly inside the earth. These rocks are coarse grained as they have enough time to form granules or crystals. Diorite, granite, pegmatite are examples of intrusive igneous rocks. Based on the silica content, igneous rocks are divided into two types. Acidic, they have high silica content 60 to 80%. They constitute the shale part of the earth crust. This means it contains aluminum. They lack iron and magnesium. They are hard rocks and hence less prone to erosion. Example granite, shale. Basic. They have low silica content 45 to 60%. These rocks are dark in color as they contain more iron and magnesium. It can be easily eroded. Example basalt. Characteristics of igneous rocks. The igneous form of rocks does not include any fossil deposit. Most of the igneous forms include more than one mineral deposit. They can be either glassy or coarse in appearance. These usually do not react with acids. They do not have strata layers like sedimentary rocks. Sedimentary rocks, igneous, sedimentary, and metamorphic rocks on the Earth's surface are exposed to denudational agents, wind, water, etc., and are broken up into various sizes of fragments, sediments. These fragments are transported by different exogenous agents and deposited. With time, more layers pile up and press down the lower layers. These layers through compaction turn into rocks. This process is called lithification. The layers of deposits of many sedimentary rocks retain their characteristics even after lithification. Hence, we see a number of layers of varying thickness is in sedimentary rocks like sandstone, shale, etc. Limestone, chalk, clay, sandstone, shale are some examples of sedimentary rocks. They also include rocks made from newly formed organic matter, both plant, biomass, and invertebrates. Characteristics of sedimentary rocks. It is believed that around 75% of the surface area of Earth is covered by sedimentary rocks. In several sedimentary rocks, the layers of deposits maintain their characteristics even after lithification. They have layered structure and are also called stratified rocks. The rocks may be coarse or fine grained, soft or hard. Cross-bedded. The sedimentary structures known as cross-bedding are the near horizontal units that are internally composed of inclined layers. They have high porosity and permeability. They are relatively poor in metallic minerals. They often contain fossil fuels. Types of sedimentary rocks. Sedimentary rocks are composed of sediments which may be clastic, chemically precipitate, or organic. Organic sedimentary rocks, chemical sedimentary rocks, classic sedimentary rocks. Depending upon the mode of formation, sedimentary rocks are classified into three major groups. Mechanically formed clastic rocks. These are formed from the accumulation of materials derived from other rocks which have been cemented together. Clastic means composite of rock and or mineral fragments. Example: sandstone, conglomerate, sorry, conglomerate, limestone, shale, loess, etc. Organically formed. These are formed from the organic material, that is, from the remains of living and dead organisms and plants. We often find natural gas and petroleum in pores of a thick sedimentary rock layer, such as in a porous sandstone. Example: geyserite, chalk, limestone, coal, etc. Chemically formed. These rocks are precipitated chemically from solutions of one kind or another. For example, they are formed when inorganic mineral compounds precipitate from a salt water solution from sea or salty inland lakes. Example: chert, limestone, halite, gypsum, potash, and nitrates, etc. Metamorphic rocks. The word metamorphic means change of form. They are the transformation of pre-existing rocks. Formation of metamorphic rocks. These rocks form under the action of pressure, volume, and temperature changes. During metamorphism, rocks sedimentary, igneous, metamorphic are forced down to lower levels by tectonic processes or when molten magma rising through the crust comes in contact with the crustal rocks or the underlying rocks are subjected to great amounts of pressure from overlying rocks. Metamorphism is a process by which rocks undergo recrystallization and reorganization of materials within original rocks. For example, extreme heat and pressure transform shale into slate or shit, sandstone into quartz, limestone into marble, and igneous rocks or clastic sediments into gneiss. Types of metamorphism. Dynamic metamorphism. It is mechanical disruption and reorganization of the original minerals within rocks due to breaking and crushing without any appreciable chemical changes. Thermal metamorphism. The materials of rocks chemically alter and recrystallize due to thermal metamorphism. There are two types of thermal metamorphism: contact metamorphism and regional metamorphism. Contact metamorphism, when a rock comes in contact with a not intruding magma and lava, and then rock materials recrystallize under high temperatures. Regional metamorphism, the rocks experience recrystallization due to deformation caused by tectonic shearing together with high temperature or pressure or both. Characteristics of metamorphic rocks: foliation or lineation during metamorphism. In some rocks, grains or minerals get arranged in layers or lines. Such an arrangement of minerals or grains in metamorphic rock is known as foliation or lineation. Banding: when minerals or materials of different groups are arranged into alternating thin to thick layers appearing in light and dark shades. Such a structure in metamorphic rock is known as banding, and rocks displaying banding are called banded rocks. Metamorphic rocks tend to be more resistant to weathering than their parent rocks because the heat and pressure welds their mineral grains together and may transform their minerals into stronger forms. Metamorphic rocks may be previous or impervious. Metamorphic rocks are classified into two major groups: foliated rocks, examples slates, gneiss, schists, etc., and non-foliated rocks, quartzites, marbles, serpentines, etc. During metamorphism, fossils are destroyed and hence they do not contain fossil fuels. Rock cycle. Rocks do not remain in their original form for long but may undergo transformation from one class to another in the cycle of rock change. This cycle, operating over the geological timescale, involves various physical, chemical, and biological processes that create, transform, and recycle the crustal minerals. You can see here rock cycle. Sedimentary rock, heat and pressure, metamorphic rock, melting, magma, cooling, igneous rocks or melting, weathering and erosion, sediments, compacting and cementing, weathering and erosion, heat and pressure. Landforms and their evolution. Introduction. Geomorphology is a science that studies landforms on the Earth's surface and involves interpretive descriptions of landforms, their origins, development, and processes associated with them. A landform is any physical feature of the Earth's surface. The surface of the Earth exhibits a great assemblage of physical features like mountain, valley, plain, plateau, hill. Each of these features has a form, structure, and Peculiar dynamics. Over the period of time, various processes, both the endogenetic and exogenetic, have reshaped these landforms to get their present form. A landscape is the visible feature of an area of land, its landforms, and how they integrate with natural or man made features. Several related landforms together make up landscapes, large tracts of Earth's surface. Every landmass passes through stages of development, somewhat comparable to the stages of life, youth, mature, and old age. Landforms, once formed, may change in their shape, size, and nature slowly or fast due to continued action of geomorphic processes and agents. In this chapter, we will talk about the landforms created by external geomorphic agents, namely running water, groundwater, glaciers, oceanic waves, and current and wind. Landforms created by running water. Running water. Humid regions receive heavy rainfall. Running water both over land flow on land surface as a sheet and linear flow as streams and rivers is the most important of the geomorphic agents which brings changes in landforms. Most of the running water erosional landforms are associated with vigorous and youthful rivers flowing over steep gradients. River streams over steep gradients eventually turn gentle due to continued vertical and horizontal erosion lateral. After channel broadening and breaking into plains, rivers lost their velocity, facilitating active deposition. There may be some depositional forms associated with the streams flowing over steep slopes, but on a small scale compared to those associated with medium to gentle slopes. The gentler the river channels in gradient or slope, the greater is the deposition. Downward cutting is less dominant and lateral erosion of banks increases on gentler slopes, and as a consequence, the hills and valleys are reduced to plains. Overland flow. Because of the sheer friction of the column of flowing water, overland flows picks up mineral particles ranging from fine clay to coarse sand depending upon how fast the flow moves. This causes sheet erosion with materials removed from the surface in the direction of a flow, leading to the formation of small and narrow rills. These rills over time develop into long and wide gullies. The gullies with continuous erosion with further deepen, widen, lengthen, and unite to give rise to a network of valleys. Soil erosion occurs when overland flow transports soil particles downslope. Erosion is greatest on bare slopes, whereas over vegetation cover greatly reduces soil erosion. Take a look at this image. Rill. Take a look at this image. Rill and gully. Running water as streams and flows. The characteristics of each of the stages of landscapes developing in running water regimes may be summarized as follows. Youth. Few streams with poor integration and flow over original slopes show shallow V-shaped valleys with no floodplains or with very narrow floodplains along trunk streams. Streams divides are broad and flat with marshes, swamp and lakes. Meanders are usually not there, and if present develop over these broad upland surfaces, these meanders may eventually entrench themselves into the uplands. Waterfalls and rapids may exist where local hard rock bodies are exposed. Mature streams are plenty with good integration. The valleys are still V-shaped but deep. The flat and broad interstream areas and swamps and marshes of youth disappear and the stream divides turn sharp. Waterfalls and rapids disappear. Old. Smaller tributaries during old days are few with gentle gradients. Streams meanders freely over vast floodplains, showing natural levees, oxbow lakes, etc. Divides are broad and flat with lakes, swamps, and marshes. Most of the landscape is at or slightly above sea level. Erosional landforms. Once overland flow is channeled into a stream, it erodes in various ways depending on the nature of channel materials, debris stream is carrying, the speed of stream and volume of the flow. Valleys. The rills will gradually develop into long and wide gullies. The gullies will further deepen, widen and lengthen to give rise to valleys. There are different types of valleys depending upon dimensions and shape like V-shaped valley, gorge, canyon, etc. can be recognized. Valley types depend upon the type and structure of rocks in which they form. George Canyon, a deep valley with very steep to straight slides. Canyon. A canyon is a variant of gorge characterized by steep step-like side slopes and may be as deep as a gorge. Gorge, almost equal in width at its top as well as its bottom. Canyon, wider at its top than at its bottom. Gorges are usually formed in hard rocks. Canyons are commonly formed in horizontal bedded sedimentary rocks. Potholes and plung pools. Potholes. These are found over the rocky beds of hill streams. Potholes are more or less circular depressions. They are formed due to stream erosion aided by the abrasion mechanical wear of rock fragments. Plung pools. Once a depression or pothole forms, it receives pebbles and boulders which were rotated by flowing water continuously, and consequently the depressions grow in dimensions. These depressions may join to become larger depressions and the valley gets depended. At the foot of waterfalls also large, deep and wide potholes form because of the sheer impact of water and rotation of boulders. Such large and deep holes at the base of waterfalls are called plung pools. Incised or entrenched meanders. Lateral erosion is more fervent on gentle slopes due to the lateral erosion. Streams develop sinuous or meandering courses. This is why we find meandering courses over floodplains and delta plains where stream gradients are very gentle. But very deep and wide meanders can also be found cut in hard rocks. Such meanders are called incised or entrenched meanders. Where rapid uplift causes meandering rivers to cut deeply into bedrock, entrenched meanders are formed. We don't find meanders in streams that flow rapidly over steep gradients as normally. Erosion is concentrated on the bottom of the stream channel. Also, steep gradient streams do more vertical erosions than lateral erosion. River terraces. River terraces are basically products of erosions as they result due to vertical erosion by the stream into its own depositional floodplain. As a river lowers its bed, it can leave behind parts of its floodplain at a higher level as a series of alluvial terraces. They may be found as with time the level of water might have decreased or sedimentation or upliftment of a rock mass. This is why they mark old valley floors or floodplains levels. There can be a number of such terraces at different heights indicating former riverbed levels. Pair terraces. The river terraces on either side of the rivers occur at the same elevation. They are called pair terraces. Depositional landforms. Alluvial fans. Alluvial fans are formed when stream flowing from higher levels break into foot slope plains of low gradient. When streams flow over mountain slopes, they do more vertical erosions and hence carry very coarse load. This load is too heavy for the streams to carry over gentle gradients and gets dumped and spread as a broad load to high cone shaped deposit called alluvial fan. The streams flowing on these fans may distribute, forming mini channels called distributaries. Alluvial fans in humid areas show normally low cones with gentle slopes from head to toe, and they appear as high cones with steep slopes in arid and semi arid climates. A pediment is a gently sloping erosion surface or plane of low relief formed by running water in an arid or semi-arid region at the base of a receding mountain front. Deltas. When the river reaches its old stage, that is, it is about to enter a lake or sea or ocean, its load carrying capacity decreases. The load carried by it is dumped and spread near the sea. If this load is not carried away far into the sea or distributed along the coast, it spreads and accumulates as a low cone. This is why deltas are often like alluvial fans but develop at a different location. But unlike alluvial fans, the deposits making up deltas are very well sorted with a clear stratification. The coarest heavy materials settle out first and the finer light fractions like silts and clays are carried out into the sea. As the delta grows, the river distributaries continue to increase in length and the delta continues to build up into the sea. Floodplains. Floodplains is a major landform of river deposition. Large sized materials are deposited first when the stream channel breaks into a gentle slope. Thus, normally, fine sized materials like sand, silt, and clay are carried by relatively slow moving waters in gentler channels using found in the plains and deposited over the bed and when the waters spill over the banks during flooding above the bed. A river bed made of river deposits is the active floodplain. The floodplain above the bank is an inactive floodplain. Inactive floodplain above the banks basically contain two types of deposits: flood deposits and channel deposits. In plains, channels shift laterally and change their courses, occasionally leaving cut-off courses which get filled up gradually. Such areas over floodplains built up by abandoned or cut-off channels contain coarse deposits. The flood deposits of spilled waters carry relatively finer materials like silt and clay. The floodplains in a delta are called delta plains. Natural levees. Natural levees and point bars are some of the important landforms found associated with the floodplains. Natural levees are found along the banks of large rivers when the velocity of the water flowing away from the bank and across the floodplain decreases. The sediment begins to settle out. Sand and silt accumulate first, building up levees along the channel. Levees are low, linear, and parallel ridges of coarse deposits along the banks of rivers, quite often cut into individual mounds. Further away, fine sediment settles out of the nearly stagnant water accumulating between the levees and the bluffs that bound the floodplain, an area known as the Back's Swamp. Here you can see point bars, floodplain, natural levee. On the second picture, natural levees source from NCRT. You can clearly see here meander neck, floodplain, bluffs. Point bars. Point bars are also known as meander bars. They are found on the concave side of meanders of large rivers and are sediments deposited in a linear fashion by flowing waters along the bank. They are almost uniform in profile and in width and contain mixed sizes of sediments. Meanders. Meanders is not a landform but is only a type of channel pattern. In large flood and delta plains, rivers rarely flow in straight courses. Loop-like channel patterns called meanders develop over flood and delta plains. This happens because of various reasons. Propensity of water flowing over very gentle gradients to work laterally on the banks. Unconcentrated nature of alluvial deposits making up the banks with many irregularities which can be used by water exerting pressure laterally. Coriolis force acting on the fluid water, deflecting it like it deflects the wind. When the gradient of the channel becomes extremely low, water flows leisurely and starts working laterally. Slight irregularities along the bank slowly get transformed into a small curvature in the banks. The curvature deepens due to deposition on the inside of the curve and erosion along the bank on the outside. If there is no deposition and no erosion or undercutting, the tendency to meander is reduced. Normally, in meanders of large rivers, there is active depositism along the concave bank and undercutting along the convex bank. The concave bank is known as cutoff bank, which shows up as a steep scarp, and the convex bank presents a long, gentle profile. As meanders grow into deep loops, the same may get cut off due to erosion at the inflection points and are left as oxbow lakes. Braided channel. Braided channels develop in rivers with a lot of sedimentary load, a steep gradient, and where the discharge of the river changes regularly. When the volume of load exceeds the river's capacity or the discharge of the river drops, the river is forced to deposit its load in the channel and islands of sediments eyots form. Landforms created by groundwater karst topography. The two processes of solution and precipitation are active in limestones or dolomites regions, occurring either exclusively or interbredded with other rocks. Any limestone or dolomitic region showing typical landforms produced by the action of groundwater through the processes of solution and deposition is called karst topography. Named after the typical topography develops in limestone rocks of karst region in the Balkans adjacent to Adriatic Sea. The karst topography is also characterized by erosional and depositional landforms. Erosional landforms, pools, sinkholes, lapis, and limestone pavements. Small to medium sized round to sub-rounded shallow depressions called swallow holes form on the surface of limestones through solution. Sinkholes are very common in limestone crashed areas. A sinkhole is an opening more or less circular at the top and funnel shaped towards the bottom with sizes varying in area from a few square meters to a hectare and with a depth from a less than half a meter to 30 meters or more. Some sinkholes form solely through solution action, solution sinks, and others might start as solution forms first, and if the bottom of a sinkhole forms the roof of a void or cave underground, it might collapse, leaving a large hole opening into a cave or a void below. Collapse sinks. Quite often, sinkholes are covered up with soil mantle and appear as shallow water pools. Anybody stepping over such pools would go down like it happens in quicksands in deserts. The term doline is sometimes used to refer to the collapsings. Solution sinks are more common than collapsings. Quite often the surface runoff simply goes down shallow and sinkholes and flows as underground streams and reemerge at a distance downstream through a cave opening. When sinkholes and dolines join together because of slumping of materials along their margins or due to roof collapse of caves, long, narrow to wide trenches called valley sinks or Uvalas form. Gradually, most of the surface of the limestone is eaten away by these pits and trenches, leaving it extremely irregular with a mass of points, grooves, and ridges or lapis. Especially these ridges or lapis form due to differential solution activity along parallel to subparallel joints. The lapi field may eventually turn into somewhat smooth limestone pavements. Here you can see the image of shallow hole in section, sinkhole in section, section of collapsed sink, cave and cave, cave in section, static pillar, cave, stalagmite, cave mouth, sinkholes, valley sinks, uvalas. Caves in areas where there are alternating beds of rocks, shales, sandstones, quartzites with the limestones or dolomites in between, or in areas where limestones are dense, massive, and occurring as thick beds, cave formation is prominent. Water percolates down either through the materials or through cracks and joints and moves horizontally along budding plants. It is along these budding plants that the limestone dissolves in long and narrow to wide gaps called caves result. Caves normally have an opening through which cave streams are discharged. Caves have openings at both the ends are called tunnels. Depositional landforms. Many depositional forms develop within the limestone caves. The chief chemical in limestone is calcium carbonate, which is easily soluble in carbonated water, carbon dioxide absorbed rainwater. This calcium carbonate is deposited when the water carrying it in solution evaporates or loses its carbon dioxide as it trickles over rough rock surfaces. Stalactites, stalagmites, and pillars. Stalactites hang as eagles of different diameters. Normally, they are broad at their bases and taper towards the free end, showing up in a variety of forms. Stalagmites rise up from the floor of the caves. In fact, stalagmites form due to dripping water from the surface or through the thin pipe of the stalactite immediately below it. Stalagmites may take the shape of a column, a disc with either a smooth, rounded, bulging end or a miniature crater-like depression. The stalagmite and stalactites eventually fuse to give rise to columns and pillars of different diameters. Landforms created by glaciers. Glaciers. Masses of ice moving as sheet over the land. Continental glacier or Piedmont glacier. If a vast sheet of ice is spread over the plains at the foot of mountains, or as linear flows down the slopes of mountains in broad throw-like valleys, mountain and valley glaciers are called glaciers. The movement of glaciers is slow. Unlike water flow, the movement could be a few centimeters to a few meters a day or even less or more. Glaciers move basically because of the force of gravity. Erosion by glaciers is tremendous because of friction caused by sheer weight of the ice. The material plucked from the land by glaciers, usually large sized angular blocks and fragments, get dragged along the floors or sides of the valleys and cause great damage through abrasion and plucking. Glaciers can cause significant damage to even unweathered rocks and can reduce high mountains into low hills and plains. As glaciers continue to move, debris gets removed, divides get lowered, and eventually the slope is reduced to such an extent that glaciers will stop moving, leaving only a mass of low hills and vast outwash plains along with other depositional features. Erosional landforms. Cirques are the most common of landforms is glaciated mountains, The cirques quite often are found at the heads of glacial valleys. The accumulated ice cuts these circuits while moving down the mountain tops. Cirques are deep, long, and wide throat or basins with a very steep concave to vertically dropping high walls at its head as well as sides. A lake of water can be seen quite often within the cirques after the glacier disappears. Such lakes are called cirque or tarn lakes. There can be two or more cirques, one leading into another down below in a stepper sequence. Horns and serrated ridges. Horns form through headward erosions of the cirque walls. If there if three or more radiating glaciers cut headward until their cirques meet high, sharp, pointed and steep-sided peaks called horn form. Horns form. The divides between cirque side walls or head walls get narrow because of progressive erosion and turn into serrated or saw-toothed ridges, sometimes referred to as arrays with very sharp crest and a zigzag outline. Glacial valleys troughs. Glaciated valleys are trough like an U shaped with broad floors and relatively smooth and steep sides. The valleys may contain littered, littered debris or debris shaped as moraines with a swampy appearance. There may be lakes gouged out of the rocky floor or formed by debris within the valleys. There can be hanging valleys at an evolution on one or both sides of the main glacial valley. The faces of divides or spurs of such hanging valleys opening into main glacial valleys are quite often truncated to give them an appearance like triangular facets. Very deep glacial troughs filled with sea water and making up shorelines in high latitudes are called fjords. Depositional landforms. The unassorted coats and fine debris dropped by the melting glaciers is called glacial till. Most of the rock fragments in till are angular to subangular in form. Streams formed by melting ice at the bottom, sides or lower ends of glaciers see some amount of rock debris small enough to be carried by such meltwater streams is washed down and deposited. Such glaciofluvial deposits are called outwash deposits. Unlike till deposits, the outwash deposits are roughly stratified and assorted. The rock fragments in outwash deposits are somewhat rounded at their edges. Moraines, they are long ridges of deposits of glacial till. Terminal moraines are long ridges of debris deposited at the end toe of the glaciers. Lateral moraines form along the sides parallel to the glacial valleys. The lateral moraines may join a terminal moraine forming a horseshoe shaped ridge. There can be many lateral moraines on either side in a glacial valley. These moraines partly or fully owe their origin to glaciofluvial waters pushing up materials to the sides of glaciers. Many valley glaciers retreating rapidly leave an irregular sheet of till over their valley floors. Such deposits varying greatly in thickness and in surface topography are called ground moraines. The moraine in the center of the glacial valley flanked by lateral moraines is called medial moraine. They are imperfectly formed as compared to lateral moraines. Sometimes medial moraines are indistinguishable from ground moraines. Eskers. When glaciers melt in summer, the water flows on the surface of the ice or steeps down along the margins or even moves through holes in the ice. These waters accumulate beneath the glaciers and flow like streams in a channel beneath the ice. Such streams flow over the ground, not in a valley cut in the ground, with ice forming its banks. Very coarse materials like boulders and blocks, along with some minor fractions of rock debris carried into this stream, settle in the valley of ice beneath the glaciers, and after the ice melts can be found as a sinus ridge called esker. Outwash plains. The plains at the foot of the glacial mountains or beyond the limits of continental ice sheets are covered with glaciofluvial deposits in the form of broad flat alluvial fans which may join to form outwash plains of gravel, silt, sand and clay. Drumlins. Drumlins are smooth, oval-shaped ridge-like features composed mainly of glacial till with some masses of gravel and sand. The long axes of drumlins are parallel to the direction of ice movement. Drumlins give an indication of direction of glacier movements. They may measure up to 1 kilometer in length and 30 meters or so in height. One end of the drumlins facing the glacier called the Stoss end is blunter and steeper than the other end called tail. The drumlins form due to dumping of rock debris beneath heavily loaded ice through fissures in the glacier. You can see in this diagram drumlins, outwash plain, esker, drumlin, terminal, moraine. Landforms created by waves and currents. Some of the changes along the coast take place very fast. At one place, there can be erosion in one season and deposition in another. Most of the changes along the coasts are accompanied by waves. Constant impact of breaking waves drastically affected the coasts. Storm waves and tsunami waves can cause far reaching changes in a short period of time than normal breaking waves. As the wave environment changes, the intensity of the force of breaking waves changes. Other than the action of waves, the coastal landforms depend upon the configuration of land and seafloor, whether the coast is advancing, emerging seaward, or retreating, submerging landward. Assuming sea level to be constant, two types of coasts are considered to explain the concept of evolution of coastal landforms. High, rocky coasts, submerged coasts; low, smooth and gently sloping sedimentary coasts, emerged coasts. High rocky coast. Along the high rocky coast, rivers appear to have been drowned with a highly irregular coastline. The hillsides drop off sharply into the water. Shores do not show any depositional landforms entirely. Erosion features dominate. Cliffs. Along a high rocky coast, waves break with great force against the land, shaping the hillsides into cliffs. Wave cut terrace. With the constant pounding by waves, the cliffs recede, leaving a wave cut platform in front of the sea cliff. Waves gradually minimize the irregularities along the shore. The materials which fall off and removed from the sea cliffs gradually breaks into smaller fragments and roll to roundness will get deposited offshore. After a considerable period of cliff development and retreat, when the coastline turns somewhat smooth with the addition of some more material to this, a wave-built terrace would develop in front of a wave-cut terrace. Bars and barrier bars. As the erosion along the coast takes place, a good supply material becomes available to longshore currents and waves to deposit them as beaches along the shore and as bars, long ridges of sand and or shingle parallel to the coast. In the near shore zone, bars are submerged features, and when bars show up above water, they are called barrier bars. Barrier bar which gets keyed up to the headland of the bay is called a spit. Lagoon. When barrier bars and spits form at the mouth of a bay and block it, a lagoon forms. The lagoons would gradually get filled up by sediments from the land, giving rise to a coastal plain. Low sedimentary coasts. Along low sedimentary coasts, the rivers appear to extend their length by building coastal plains and deltas. The coastline appears smooth with the occasional incursions of water in the form of lagoons and tidal creeks. The land slopes gently into the water, marshes and swampy may bound along the coast. Depositional features dominate when waves break over the gently sloping sedimentary coast. The bottom sediments get churned and move readily, building bars, barrier bars, spits, and lagoons. Lagoons would eventually turn into a swamp, which would subsequently turn into a coastal plain. The maintenance of these depositional features depends upon the steady supply of material. Storm and tsunami waves cause drastic changes irrespective of supply of sediments. Erosional landforms, cliffs, terraces, caves, and stacks. Wave-cut cliffs and terraces are two forms usually found where erosion is the dominant shear process. Almost all sea cliffs are steep and may range from a few meters to 30 meters or even more. At the foot of such cliffs, there may be a flat or gently sloping platform covered by rock debris derived from the sea cliff behind. Such platforms occurring at elevations above the average height of wave is called a wave-cut terrace. The lashing of waves against the base of the cliff and the rock debris that gets smashed against the cliff along with lashing waves create hollows, and these hollows get widened and deepened to form sea caves. The roofs of caves collapse and the sea cliffs recede further inland. Retreat of the cliff may leave some remnants of rock standing isolated as small islands just off the shore. Such resistant masses of rock, originally parts of a cliff or hill, are called sea stacks. Like all other features, sea stacks are also temporary and eventually coastal hills and cliffs will disappear because of wave erosion, giving rise to narrow coastal plains and with the onrush of deposits from over the land behind may get covered up by alluvium or may get covered up by shingle or sand to form a wide beach. Here you can see erosional landforms of sea wave. Here first off you see wave cut platform, blowhole, bay, beach, bay, sea cave, natural bridge, headland, sea stacks, bay, headland. Depositional landforms, beaches. These are characteristics of shorelines that are dominated by deposition but may occur as patches along even the rugged shores. Most of the beaches are made up of sand-sized materials, and these sand-sized materials making up the beaches comes from land carried by the streams and rivers or from water erosion. Beaches are temporary features. Shingle beaches, beaches which contain excessively small pebbles and cobbles, dunes. Just behind the beach, the sands lifted and winnowed from over the beach surfaces will be deposited as sand dunes forming land ridges parallel to the coastline are very common along low sedimentary coasts. Bars, a ridge of sand and shingle formed in the sea in the offshore zone from the position of low tide waterline to seaward, lying approximately parallel to the coast is called an offshore bar. Barriers. An offshore bar which is exposed due to further addition of sand is termed a barrier bar. The offshore bars are barriers commonly formed across the mouth of a river or at the entrance of a bay. Spits. Sometimes such barrier bars get keyed up to one end of the bay when they are called spits. Spits may also develop attached to headlands or hills. Lagoons. The barriers, bars, and spits at the mouth of the bay gradually extend, leaving only a small opening of the bay into the sea, and the bay will eventually develop into a lagoon. The lagoons get filled up gradually by sediment coming from the land or from the beach itself, aided by wind, and a broad and wide coastal plain may develop, replacing a lagoon. Here you can see depositional landforms of sea wave, longshore current, bay, sand split, bay, mouth bar, lagoon, bay, inlet, barrier island, beach, tombolo, sea island. Landforms created by winds. Wind is one of the two dominant agents in hot deserts. The desert floors get heated up too much and too quickly because of being dry and barren. The heated floors heat up the air directly above them and result in upward movements in the hot lighter air with the turbulence, and any obstructions in its path sets up eddies, whirlwinds, updrafts, and downdrafts. Winds also move along the desert floors with a great speed, and the obstructions in their path create turbulence. The wind action creates a number of interesting erosional and depositional features in the deserts. Erosional landforms, pediments, and pediplains. Landscape evolution is deserts is primarily concerned with the formation and extension of pediments. Gently inclined rocky floors close to the mountains at their foot, with or without a thin cover of debris, are called pediments. Such rocky floors form through the erosions of mouth from front through a combination of lateral erosion by streams and sheet flooding. Erosion starts along the steep margins of the landmass or the steep sides of the tectonically controlled steep incision features over the landmass. Once pediments are formed with a steep wash slope followed by a cliff or free face above it. The steep wash slope and free face retreat backwards. This method of erosion is termed as parallel retreat of slopes through backwasting. So, through parallel retreat of slopes, the pediments extend backwards at the expense of the mountain front, and gradually the mountain gets reduced, leaving an Inselberg, which is a remnant of the mountain. That's how the high relief in desert area is reduced to low featureless plains called peneplains. Playas. Plains are by far the most prominent landforms in the deserts. In deserts, the drainage is towards the center of the basin, and due to gradual deposition of sediments from the basin margins, a nearly level plain forms at the center of the basin. In times of sufficient water, this plain is covered up by a shallow water body. Such types of shallow lakes are called playas, where water is retained only for short duration due to evaporation, and quite often the playas contain good deposition of salts. The playa plain covered up by salts is called alkali flats. Deflation halos and caves. Deflation halos are shallow depressions created by weathered mantle from over the rocks or bare soil gets blown out by persistent wind or movement in one direction. Deflation also creates numerous small pits or cavities over rock surfaces. The rock faces suffer impact and abrasion of wind-borne sand, and first shallow depression called blowouts are created, and some of the blowouts become deeper and wider fit to be called caves. Mushroom, table, and pedestal rocks. Many rock outcrops in desert easily susceptible to wind deflation and abrasion are worn out, mainly leaving some remnants of resistant rocks polished beautifully in the shape of mushroom with a slender stalk and a broad and rounded pear-shaped cap above. Sometimes the top surface is broad like a tabletop, and quite often the remnants stand out like pedestals. Depositional landforms. There is good sorting of grains and depositional landforms made by wind, since wind is they're everywhere, and wherever there is a good source of sand and with a constant wind directions, depositional features in arid regions can develop anywhere. Sand dunes. Dry hot deserts are good places for sand dune formation. Obstacles to initiate dune formation are equally important. Take a look at this picture. Sand dunes. You can recognize the sum of the dunes here. Birchen, safe, parabolic, transverse, longitudinal. There can be a great variety of dune forms. Crescent-shaped dunes called barchans with the points or wings directed away from wind direction, that is downwind, form where the wind direction is constant and moderate, and where the original surface over which sand is moving is almost uniform. Parabolic dunes form when sandy surfaces are partially covered with vegetation. That means parabolic dunes are reversed barchans with the wind direction being the same. Safe is similar to Barchan with a small difference. Safe has only one wing or point. This happens when there is a shift in wind conditions. The lone wings of safes can grow very long and high. Longitudinal dunes form when supply of sand is poor and wind direction is constant. They appear as long ridges of considerable length but low in height. Transverse dunes are elegant perpendicular to wind direction. These dunes form when the wind direction is constant and the source of sand is an elongated feature at right angles to the wind direction. They may be very long and low in height. When sand is plenty, quite often the regular shaped dunes Kolsky and lost their individual characteristics. Most of the dunes in the desert shift, and a few of them will get stabilized, especially near human habitations. End of the chapter, we can see the previous year prelims questions are mentioned here. Take a look at it. Consider the following: electromagnetic radiation, geothermal energy, gravitational force, plate movements, rotation of the earth, revolution of the earth. Which of the above are responsible for bringing dynamic changes on the surface of the earth? All of the above. That means D is the answer here. Which of the following phenomena might have influenced the evolution of organisms? Continental drift, glacial cycles. Select the correct answer using the codes given below. Both 1 and 2, answer is C. Consider the following statement: the Earth's magnetic field has reversed every few 100,000 years. When the Earth was created more than 4,000 million years ago, there was a 54% oxygen and no carbon dioxide. When living organisms originated, they modified the early atmosphere of the Earth. Which of the statements given above is correct? 1 and 3 is the correct. That means C is the answer here. Take a look at the previous year mains questions. Discuss the geophysical characteristics of circum-Pacific zone. 150 words 2020. Define mantle plume and explain its role in plate tectonics. 150 words 2018. Explain the formation of thousands of islands in Indonesia and Philippines. Archipelagos. 150 words 2014. Why are the world's fold mountain systems located along the margins of continents? Bring out the association between the global distribution of fold mountains and the earthquakes and volcanoes. 150 words 2014. What do you understand by the theory of continental drift? Discuss the prominent evidence in its support. 100 words 2013. Thank you.